I would like to thank the organizers for giving me the opportunity to talk about quantitative magnetic force microscopy as an experimental tool to develop thin film systems supporting skyrmions at room temperature. I'm also looking forward to come to Cefalù and give a live talk in this very nice city. Skyrmions have been identified as the ideal information carriers in racetrack type memory devices. Now for this, the skyrmions must be small. Small skyrmions you can obtain if you have a material that has a high Jalaszynski-Moria interaction, which you can obtain by having materials that have additive DMI at the interfaces. Then we would like to have a small magnetization, which we can obtain with a ferrimagnetic material that is operated near the magnetization compensation point. Then we also must have a material that has a small skyrmion pinning, so we should have uniform film properties, which can, for example, be obtained by using amorphous materials, either amorphous ferromagnets or amorphous rare earth ferrimagnets. Then we would also like to have a rapid skyrmion transportation velocity, which it has been shown that for domain wall devices, a very high velocity could be obtained by using ferrimagnetic materials that were operated near the orbital moment compensation point. And skyrmions should move along the track, not perpendicular to it. Therefore, the skyrmion Hall effect must be suppressed. Now, this can be achieved, for example, by coupling two ferromagnetic skyrmions antiferromagnetically, or by using skyrmions in ferrimagnets that are operated near their compensation points. Fifth point is that we have to keep the distance between the skyrmions, or between the skyrmion and the absent skyrmion, constant. In this case, it's very difficult to achieve because that skyrmion may move a little faster and so fill the gap that is over here. So one way to solve this problem may be that we store the bits rather in two distinct types of skyrmions than in the skyrmion and absence of skyrmion. And so we can have a regular chain of these two different types of skyrmions and move that chain through the racetrack device. Now, a system that shows very strong additive DMI has been introduced a while ago by the group of Christos Panagopoulos. And the system they have grown is an iridium, iron, cobalt, platinum multi-layer that has additive DMI from this and that interface. Now, by tuning the thickness of these iron and cobalt layers, they were able to show that the skyrmion density can be varied over a large range. And we have also grown this system, but here with just 5 repeats. And as in the earlier work, we also observed that we can nicely tune the skyrmion densities in these materials. Further, we found that by annihilating the skyrmions by increasing the field and then recovering the skyrmions by lowering the field, the skyrmions renucleate almost always at the same position. So there is a very high return point memory in these materials. Moreover, we found that the contrast of the skyrmions depends very much on the position of the skyrmion. So, for example, these two are very bright skyrmions, and this one is a very faint one. And this can be explained by the different sizes, different diameters these skyrmions have in this material, which arises from the inhomogeneity of the material. And that inhomogeneity is a serious problem that we also discovered in iridium, cobalt, platinum multilayers. In this system, we have analyzed the average Jalaszynski-Moria DMI interaction from a domain size analysis, and we found that we have about 2 millijoules per square meter in average. But then we imaged the skyrmion with a calibrated MFM tip that allowed us to model the MFM contrast obtained at the skyrmion. And when matching the model to the skyrmion, we found that we need a D of about 3.4 to model the skyrmion in this place. So this means that at the locations of the skyrmions, we have a higher D than the average D in the material. And this is actually also the reason why we only observed a few skyrmions in this material system here. So the skyrmions only existed at this preferred location that have a high D, but this also leads to a strong pinning. So how can we solve that pinning problem? Well, one strategy that we followed is shown here. So what we did here is we grow a skyrmion generator layer. So that's one of these iridium, iron, cobalt, platinum multilayers. We grow another one up here. And in the middle, we sandwich in a rare earth ferrimagnetic layer. Now, why a rare earth ferrimagnetic layer? Because our hope was that such layers are known to have a low exchange stiffness. The anisotropy of this interlayer can be tuned by the content of terbium and gadolinium in this layer. The magnetization can be tuned by the rare earth 3E element, and possibly we can have a skyrmion in the layer here that gets imprinted in this interlayer. And because there is a very low domain wall energy in this interlayer, we hope that there is very low pinning. Now, does this concept work? Well, yes, at least partially it works. So here you show, here we have such an interlayer that is sandwiched between two of these iridium, iron, cobalt, platinum multilayers. And indeed, we find skyrmions, albeit with a lower skyrmion density than in the initial multilayer material. But if we down-tune the the anisotropy of this rare earth interlayer, we down-tune it such that it becomes actually very small, then the skyrmion density recovers. We get almost the same skyrmion density than in the initial ferromagnetic multilayer. Now, different to that system, here all the skyrmions appear with the same contrast, which means that they have a very similar diameter in different locations. Also, we find that the skyrmions can be renucleated in different positions. So we haven't fabricated devices yet from these materials, but from the MFM data I've shown you here, we can conclude that there is much lower pinning in these materials. Now, in some of these materials, and here is such an example where we have a skyrmion generator layer, a ferrimagnetic interlayer, and another skyrmion generator layer, we find two distinct types of skyrmions that we found to be very interesting. So here we have skyrmions with a strong MFM contrast together with skyrmions which have a much weaker MFM contrast. Now let me show you the field evolution of the micromagnetic state of such samples. At zero field, we observe the very typical domain phase that we have for samples with a high Jarzynski-Moria interaction. And then if you apply a magnetic field, these worm-like domains, they shrink and we form a set of skyrmions here, strong and weak skyrmions, that simultaneously exist in this material. And let me show you how the contrast of these skyrmions evolves with the applied magnetic field. And that's shown in this little graph here. Let me first guide you through the contrast evolution of the weak skyrmion. So this is a weak skyrmion observed about 130 millitesla. And now if we increase the field, we find that the contrast of these weak skyrmions becomes smaller and smaller. Now this is compatible with the shrinking of the skyrmion radius as the field is increased. Now the same is true for a strong skyrmion. So if you apply a field, also the strong skyrmion loses contrast, which we can again explain by a shrinking of the skyrmion radius. But then eventually at some critical field, this bright skyrmion, the strong contrast skyrmion, switches into the weak contrast skyrmion state. Now this critical field is not the same for all the skyrmions, but all of them switch into a weak skyrmion state. Now, how can we understand this? Let me explain you how our experimental strategy that we took to analyze the contrast of the different skyrmions. So this is our initial tri-layer sample consisting of this skyrmion generator layer at the bottom, at the top, and the intermediate ferromagnetic interlayers. Now we've grown a series of samples where we decomposed all these layers. So this is shown here. Here we have a sample that just consists of one of these Skyrmion generator layers. This means of 5 repetitions of iron cobalt. Then we grow this Skyrmion generator layer on top of a ferromagnet. We grow 2 of these Skyrmion generator layers directly on top of each other. So this is a 10 repetition of the iron cobalt bilayer. Then we grow 2 of these Skyrmion generator layers with an intermediate non-magnetic tantalum layer, and we compare these samples to this. So we have performed MFM at exactly the same tip sample distance with the same tip. How this is done technically, you can find in this reference, and we have analyzed the contrast of about 30 Skyrmions in all of the samples. So what we find shown here. For a single Skyrmion generator layer, we find a Skyrmion contrast of about 0.3 Hertz. Now, this is also true if we grow the Skyrmion layer on top of the ferromagnet. We have contrast that is reduced, probably by the non-ideal growth of this layer on top of the amorphous substrate. Now, if we grow a double layer of these Skyrmion generators, then the contrast increases to about 0.71. But let me compare this to the contrast we had in the initial sample. There we had a contrast of 0.58 for a weak Skyrmions and more than 1 Hertz for a strong Skyrmion. So very different from the contrast we observe here. Now, if you grow the 2 Skyrmion layers, but separating with a non-magnetic tantalum layer, the Skyrmion contrast is about 0.54 Hertz, which is almost identical to the 0.58 Hertz we find for the weak Skyrmions here. So we can conclude that the weak Skyrmions in our tri-layer samples are actually Skyrmions that only exist in the bottom and top Skyrmion generator layer, but not in the intermediate ferromagnetic layer. We can also conclude that the strong Skyrmion must be presumably one that penetrates through all of the layers. But in order to further analyze the micromagnetics, we have to do micromagnetic simulations, which were done by the help of Riccardo Tomasello, Giovanni Finocchio, and Dieter Süß. Now, to do this, we started with 2 initial states. So there is an initial state 1 where we imprinted the Skyrmion in the bottom ferromagnetic layers and the top ferromagnetic layers, but not in the interlayer. And there is an initial state 2 where a Skyrmion is also imprinted in the ferromagnet. Now, let me show you how these initial states evolve in a computer. So here is the evolution, the end state of the evolution of the Skyrmions. So what we find is that for this initial state, the Skyrmions still exist in all of the top 5 layers of the top Skyrmion generator. The Skyrmion radius is slightly increased. The radius depends on the position of the layer within the multi-layer stack. There is still no Skyrmion in the ferromagnet here. There is Skyrmions in the lower ferromagnetic layers, but only in the 4 bottom layers and not in the 5th layer. So in the 5th layer, although we had one initially, the Skyrmion was annihilated. Now, why was it erased? It is erased because we have a homogeneous magnetization of the ferromagnet, and that ferromagnet is strongly exchange coupled to the topmost layer of the ferromagnet. Therefore, this homogeneous magnetization also leads to a homogeneous magnetization in the ferromagnetic layer, and the Skyrmion does no longer exist. And so the situation is very different if we let evolve the second initial state. Then we have a Skyrmion penetrating through all of the layers, and in fact, the radius of the Skyrmion is much larger. So here we have a Skyrmion penetrating through all of the layers as expected, and obviously this gives a much stronger MFM contrast. Now let me show you some details about the chiralities of these Skyrmions. If we look at the chirality in the top 5 layers, we find that we have a clockwise chirality as expected for a negative TMI. Now, in the ferrimagnetic interlayer, we have an almost counterclockwise near wall chirality. But you see, the near wall chirality is slightly distorted. It's kind of bent a little bit. Now, in the topmost of the bottom ferromagnetic layers, we actually find a skyrmion that has a Bloch-type wall. Now, why do we have this Bloch-type wall there? Because in the fourth layer, we again have the counterclockwise near wall. So we conclude that the Bloch wall skyrmion appears because the skyrmion is frustrated. It has to choose between a counterclockwise chirality that exists in the ferrimagnet and the clockwise chirality we have in the fourth layer of the ferromagnet. So that skyrmion in the middle has to compromise between the two types of walls and therefore takes the form of a Bloch wall. Now, if we go through the bottom layers, they all have near walls except the bottommost skyrmion that has a counterclockwise near wall, which arises from a minimization of the magnetostatic energy. So obviously, to understand the chirality of a skyrmion and how it evolves through such a complicated multilayer stack, we must know the RKKY exchange through the platinum layer, through the iridium layer, and through double layers of the platinum iridium. Now, in our calculations we have performed for this paper, we have introduced an RKKY interaction for the platinum, but we have assumed there is no RKKY coupling through the platinum and iridium layers. There is actually also no literature data about this. So let us measure these interactions. Now, how can we measure the RKKY exchange through noble metal interlayers? Now, for antiferromagnetic RKKY, this is actually a very simple experiment. All you have to do is to grow two ferromagnetic layers that are separated by the interlayer that gives rise to antiferromagnetic RKKY. Then if you put this system in a field, let's say in an up field, then if this up field is strong enough, the lower ferromagnetic layer actually takes an orientation parallel to the up field, if the field is strong enough. So the field requires to break the exchange is actually a measure for the RKKY exchange interaction. That's how, these interactions could be measured. But how can we measure ferromagnetic interaction? In a ferromagnetic case, the two ferromagnetic layers will be parallel and an external field cannot break the exchange. So here is our strategy to measure the ferromagnetic exchange. Now, how we do that? We start with a ferrimagnetic layer. That ferrimagnetic layer has a high coercivity at room temperature, and it is built in such a way that the rare earth element dominates the 3D element. So in an up field, the rare earth element will align parallel to the field, where the 3D element remains anti-parallel to the external field. Now, an adjacent cobalt layer that we put there will then take an orientation that is parallel to that of the 3D element in the ferrimagnet. And therefore, if you have an interlayer which has ferromagnetic RKKY exchange, the so-called free cobalt layer will then also take an orientation parallel to the pin one. And now we can apply an external field, and if that external field is sufficiently strong, the free cobalt layer will take an orientation parallel to the external field and will break the ferromagnetic RKKY exchange. So by looking at the field required to switch that free layer, we have a measure for the ferromagnetic RKKY exchange. Now, there's one problem here. What can happen if this interlayer exchange coupling is very strong is that this so-called pinned cobalt layer becomes unpinned. It actually ruptures the exchange interaction at this interface. But let me show you some results. Here is the result for a platinum layer of about 2 nanometer thickness. So if you apply a very strong up field, as I said, the the rare earth element is in the up direction, but actually the cobalt layer here becomes unpinned from the 3D element orientation. It takes an up direction only if you reduce the field to about below 2 Tesla. So in this situation here, then the cobalt layer actually takes the orientation of the 3D element in the ferromagnet, whereas the free cobalt layer is still in the up state. Now, if we further reduce the field actually to this point here, then the free layer switches against the external field because we have this ferromagnetic RKKY interlayer exchange, which favors to have a parallel orientation of the two layers here. So that's this situation. So by measuring the area here, we can actually obtain a measurement of the RKKY interaction. And we have measured this for different cobalt layer thicknesses, and here are our results between 3.6 nanometer of cobalt and about 1.6, and our results agree very well with previous data published in literature. Now, to measure the RKKY exchange through this platinum layer works because the free cobalt layer is sandwiched between two platinum layers. So the DMI existing at this interface is actually compensated by the opposite DMI at that interface, and that's why this cobalt layer shows a nice rectangular loop. Now, if we want to measure the RKKY exchange here, not through a platinum layer, but if you want to measure it through an iridium layer, the situation becomes more complicated because now the cobalt layer, the free cobalt layer, is sandwiched between a platinum and an iridium layer. And therefore we get Choleshinski-Moria interaction. And because we have now a D that is not zero anymore, the magnetization, as you reduce the field of that cobalt layer, decays. It forms skyrmions and it forms stripe domains if you go to zero field. So the loop is very rounded. And now if we try to analyze such a rounded magnetization behavior, and we now couple this system to the ferromagnet, then it is very difficult to clearly see where this free cobalt layer switches. It's very difficult to determine the Choleshinski-Moria interaction. To determine the exchange interaction through the iridium interlayer. It's very difficult to do. So we have to come up with a concept to suppress the DMI and the free cobalt layer, but still keep the iridium interlayer here. So how do we do that? We split this cobalt layer into two cobalt layers and we symmetrize the interfaces. And we do that by splitting the cobalt layer and having a lower cobalt layer that is sandwiched between iridium and platinum, and having an upper cobalt layer that's now sandwiched between platinum and iridium. So these two cobalt layers, they have opposite DMI. They're exchange coupled together very strongly through this thin platinum layer, and therefore we have a suppressed DMI. So we have now suppressed DMI in this layer, and now we can measure the ferromagnetic RKKY through that iridium layer. Now, by using, just coupling through the iridium layer to ferromagnetic layers, we can also measure the antiferromagnetic branch. So here are our results. This line here, these are our results. So we can obtain the oscillatory exchange through the iridium. And please note that our results are compatible with earlier work, but in contrast to earlier work, we could also determine the ferromagnetic part of the exchange coupling. Further, we could also measure the RKKY interaction through platinum-iridium double layers, and we actually find for a 1 nanometer double layer that we have a ferromagnetic interlayer exchange of 0.25 millijoule. So it is not zero. We do have a ferromagnetic RKKY exchange, a substantial exchange through a platinum-iridium multilayers. And in future micromagnetic calculation, this interlayer exchange energy must be considered before we can say something about the skyrmion chiralities in these different layers. So let me move to the last point in my talk. I have shown you that two distinct skyrmions can exist in these triple layers here. I've also shown you that we can tune the skyrmion density in these iridium, iron, cobalt, platinum multilayers. Now, our new idea is to replace these ferromagnetic crystalline layers by ferrimagnetic amorphous layers. So we replace the iron layer by an iron terbium gadolinium layer. We replace the cobalt layer by a cobalt terbium gadolinium layer. And why we do that? First of all, we want to have an amorphous layer. Then we want to increase the layer thickness. We want to suppress M and L to have no Skyrmion Hall effect and to have a high Skyrmion transport speed. Now, does this work? That it works is shown here. So here we have the results obtained for an iridium, iron, cobalt, platinum layer, as shown you before. We have a nice high density lattice of Skyrmions. Now, if we now replace the 0.6 nanometer cobalt layer here by a cobalt ferrimagnet of the same thickness, we find the same density of the Skyrmions at about the same field, but with a somewhat reduced Skyrmion contrast. Now, this can be understood by the lower magnetization of the ferrimagnet, but we obtain about the same Skyrmion density. It's actually, we wondered, why is the Skyrmion density the same? After all, we reduced the cobalt content at the platinum interface, which supposedly reduces the Joule-Jasinski-Moria interaction at that interface. Well, it also reduces the perpendicular anisotropy, and therefore we reduce both the D and the Ku, and therefore, presumably, the copper remains roughly constant, and this may explain the roughly constant Skyrmion density in these materials. Now, we have also further reduced the cobalt content, and that's shown here. We go from 90% down to 80%. And of course, what happens is we lose magnetization, so we lose Skyrmion contrast. We also have to lower the field where the Skyrmions appear slightly, but we retain the same Skyrmion density. Now, can we also replace the iron layer by an iron rare earth ferrimagnet? Yes, we can. That's shown here. We replace the iron layer by an iron 85 terbium 15 layer, and indeed we find a Skyrmion with about the same density as in the initial layers. Then we can also increase the thickness of these layers, but unfortunately, when we increase the thickness of the iron layer here, but the same is also true if you increase the thickness of the cobalt rare earth ferrimagnet, the Skyrmion density becomes smaller and smaller, and the domains get bigger and bigger. So this shows that increasing the thickness reduces the anisotropy, but it reduces even more the D. So finally, copper goes towards 1 and maybe below 1, and that means instead of having a Skyrmion lattice, we'll end up in a situation where we have just a few isolated Skyrmions. Now, can we tune this system towards the compensation point? We attempted this by reducing the iron content and simultaneously reducing the cobalt content. So we drive both of these ferrimagnetic layers towards their compensation point. And if we do so, we can actually retain the high Skyrmion density in these materials. The contrast, of course, becomes smaller and smaller. So here the contrast is reduced by a factor of 20, which is because we reduce the magnetization by a factor of 20. But you see that we still have that same Skyrmion density. Although I have to say that the field where the Skyrmions are nucleated becomes smaller and smaller. So remember, in the iridium, iron, cobalt, platinum system, we had about 130 millitesla to generate the Skyrmions. Now here we just need 37 millitesla to generate the Skyrmions. If we further increase the rare earth content, the Skyrmion field, the field required to generate the Skyrmions, becomes smaller and smaller. And what you also see is that the MFM tip seems to mollify the Skyrmions here. Let me show you a zoomed image. Now, in the zoomed image, you see that some of the Skyrmions at the MFM images become take a very irregular shape. Actually, a zoomed version of this Skyrmion is shown here. And the tip here is scanned from the bottom to the top. And what you actually find is, instead of having a normal roundish skyrmion, we have a ring-like object here. How can we understand this ring-like object? And what happens here is, as the tip starts to scan over the skyrmion, it starts to feel the field of the skyrmion, and we get a repulsive contrast. And then as you scan towards the center of the skyrmion, the field of the tip is too large and the skyrmion is annihilated. And when the tip scans over the skyrmion, over the annihilated skyrmion, and gets further away from the location of the skyrmion actually renucleates. So the skyrmion gets deleted only when the tip is scanning over it, but it recovers as soon as the tip scans away from the skyrmion. And this shows us also that we have to perform additional work here. We, of course, while this is very interesting to modify the skyrmions with the MFM tip, we would like to have a situation where the tip does not modify the skyrmion. Now, luckily, we perform our MFM in vacuum, and we use cantilevers that have a quality factor up to 1,000,000. And therefore, we have a very high field sensitivity. We actually can measure down to about 50 microteslas per square root of hertz. So we have a sensitivity that is almost comparable to that of the best NV-centered magnetometer microscopes. Now, unfortunately, we have still a too high magnetic moment tip. So we have to reduce the magnetic moment of the tip, which is not such an easy thing to do, because at the moment we use a coating that is only 3 nanometers thick. And if you further reduce the coating thickness of the ferromagnetic layer on the tip, we found that the tips become very irreproducible. So some of the tips work, some don't. So to go further down with the layer thickness is not an option. Instead, what we're presently trying is to go to ferromagnetic alloy tips. So by alloying the ferromagnetic with the non-ferromagnetic material, we can reduce the magnetic moment of the tip. And now, having this sensitivity advantage from operation in vacuum and from the high quality factor cantilevers, we hope that we will be able to come up with a tip that gives a much weaker contrast, but still strong enough to, with our excellent signal to noise ratio, to be able to image the skyrmions, but no longer to perturb them by the tip field. Now that brings me to the summary. I've shown you that apart from creating skyrmions and 2 distinct types of skyrmions, we can now build multi-layers that consist of rare earth ferrimagnets containing iron and cobalt, that we can retain the high DMI coming from the additive DMI of the interfaces, but now having the ferrimagnetic materials here, that we can now tune the properties of these ferrimagnetic materials such that we can approach the compensation point and hopefully also the orbital moment compensation points. And of course, it becomes more difficult to observe the skyrmions experimentally, but now we have a system where we can tune the skyrmions for future devices. And with that, I would like to thank you for your attention. I hope to see you in Cefalù, where I will answer all your questions. Thank you very much.